Hello lovelies, in this video we're going to be going through your OCR Gateway Physics Paper 1 and the Separate Science Hidesy paper that we've written for 2024. So what we want you to do is to pause after each question comes up, have a go at it yourself and then play the video and we can go through everything together.
You are asked to select the value for the typical diameter of an atom. Now this is a recall question, so if you're wondering how you're meant to know this, examiner simply expects you just to know it. However, as this is a multiple choice question, we can narrow down our options. We know that atoms are very small, and therefore they won't have a positive power in standard form, because that's used for big numbers. That leaves us with 1 times 10 to the minus 5 or 1 times 10 to the minus 10. Now atoms are actually really small. So they are in fact of the order of 1 times 10 to the minus 10. Now, as this is a fact that we need to know, this is the perfect opportunity, if you don't know this, to get out your notes, to get out a flashcard, write on one side of that flashcard what is the typical diameter of an atom, and on the other side of it write 1 times 10 to the minus 10 meters, and then you're guaranteed to get this right next time. A force of 32 newtons is applied to a spring. The spring stretched and had an extension of 5 centimetres. Now we're asked to calculate the spring constant. So to be able to answer this, we need to know the equation. We should know that the force exerted by a spring is going to be equal to the extension multiplied through by the spring constant. So that's our equation that we're going to use here. Now if we look through the information that we've been given, you can see we've been told the force that's exerted by the spring, that is equal to 32 newtons. And we know the extension is 5 centimetres. This is where our first problem pops up here. Remember that in physics we use metres, we don't use centimetres. So in this case we need to convert the extension from 5 centimetres to metres. And we do that simply by dividing through by 100. So extension here that we're going to use is 0.05. So if we look at the question, you can see we're being asked to find the spring constant. So that means that as this isn't already the subject of this equation, we need to rearrange the equation. Spring constant therefore will be equal to that force divided by the extension. So if we now substitute in the relevant numbers, we'll get 32 divided by 0.05. And that gives us an answer equal to 640 Newton per meters. And of course, that is our answer. So A is our answer. So we'll put in our box A. A 0.1 kilogram block of ice was melted. We're told here that the specific latent heat of fusion of water is 330 kilojoules per kilogram, and we're asked to calculate how much energy is required to melt the 0.1 kilogram block of ice. So first things first here is we need to identify what equation we need. We're talking about specific latent heat in this question, and we only have one equation in physics that we're going to use for that. And that is that the change in thermal energy is equal to the mass times by the specific latent heat. So there is our equation there. Now the energy that we're being asked to find is going to be that change in thermal energy. Now looking at what they've given us, I can see they've given me the specific latent heat, in this case of fusion. However, they've given it as 330 kilojoules per kilogram. Now this is really sneaky here, because we need it to be in joules per kilogram, not kilojoules per kilogram. So to convert from kilojoules to joules, we times through by 1000. So that gives us 330,000 joules per kilogram. So there we go, we've got that now. We also know that the mass is simply 0.1 kilogram. That is in our standard units for mass, so we're happy with that. So now we're going to have 0.1 times by 330,000. And that leaves us with our energy of 33,000 joules. And looking at the answer options, I can see that B is 33,000 joules So I'm going to write B in my answer box. You can see there though that if you miss the fact that it was kilojoules per kilogram, then we would get a completely different answer. So please do be so careful of the units in physics. It's almost like they're being really sneaky and trying to trip you up, so don't fall into that little pitfall. Identify the scalar quantity in the following options. So here we've got velocity, acceleration, distance and displacement. Now this is just a fact recall question. We just need to know which of these are vectors and which are scalars. Velocity is of course a vector. Acceleration is also a vector because we can accelerate and decelerate. However, distance is a scalar. Displacement is the vector version of distance. However, distance is the scalar. So our answer here is C. Just to remind you before we go on to the next question, the difference between a vector and a scalar is that a vector shows magnitude or size and direction, whereas a scalar just shows that magnitude. It doesn't tell you which direction we're going in or if it's negative or positive, for instance. So distance is the scalar version of displacement. We just know how far we've gone, not whether we've gone left, right, up or down. Two people, A and B, sat on either side of a seesaw. Person A has a weight of 600 newtons. So let's draw that on then. We've got this downward force at A of 600 newtons. We're told that the seesaw was in equilibrium, and we're asked to calculate the weight of person B. Now, the important thing here is that the seesaw is in equilibrium. That means that the clockwise moments are equal to the anti-clockwise moments. Let's remind ourselves of the equation for a moment of a force. So the moment of a force is equal to the force times by the distance from the pivot to that force. And that distance always needs to be at right angles to the force. So now we've reminded ourselves of what the equation for the moment of a force is, let's write down that rule that we mentioned that the equilibrium fact tells us. So we know that the sum of all of the clockwise moments is going to be equal to the sum of all of the anti-clockwise moments. So now that we know this rule, what we need to do is to have a good look at our diagram and work out which forces are going to cause clockwise moments and which forces will cause anti-clockwise moments. So let's start by looking at B. So B has a weight as well. And imagine around that pivot, what's going to happen is the seesaw is going to go around in a clockwise direction. Whereas the person at A, again, if you think of that seesaw, it's going to go down, which is effectively moving in an anti-clockwise direction. If we work out the moments of each, so the anti-clockwise moments are 600 times by 1.4, and that's equal to the clockwise moments, which will be B times by 0.8. Now, rearranging this, I can find out what B is now by dividing by that 0.8. So B is 600 times 1.4 divided by 0.8, which gives us 1,050 newtons, which is going to be the weight of person B. A current of 0.1 amps passes through a 20 kilo ohm resistor. Here we're asked to calculate the power dissipated. So first things first, let's have a think about what we know already so we can work out our equation. We know that we need to find the power, we're given a current, and we're given a resistance. That means if we look through the equations that we know, we can use the one that states that power equals current squared times by resistance. Now we know current is equal to 0.1 amps, whereas resistance is 20 kilo ohms. However, we've got that problem again of how in physics, we don't want things as kilo or whatever, we just want ohms in this case. So we need to convert the 20 kilo ohms to ohms by just timesing through by 1000. So that means we have a resistance equal to 20,000 ohms. Plugging these numbers in now to our equation, we find that power equals 0.1 squared times by 20,000. Now popping that into a calculator, I get 200 watts. So our answer here will be D, 200 watts. The diagram below shows the electric field pattern between two charges X and Y. Here we're asked to identify the correct charges for X and Y. And to do this, the fact that we really need to know is that electric fields move from positive to negative charges. So when we see the direction of these arrows here, we can see that it's moving away from X, but it's moving towards Y. Now that tells us that X has to be X, so we can cross out the negative options, and that Y has to be negative. And so as a result, our answer must be C. So C is our answer, and it is that simple. We just need to use the fact electric fields go in the direction from positive to negative charges. Component X was connected to a circuit. As the temperature was changed, the resistance also changed. The relationship between temperature and resistance is shown on the graph below. And here you can see that as the temperature gets bigger, the resistance gets smaller. Now this must mean that we have some sort of a temperature-dependent resistor. So we need to remember what the name of a temperature-dependent resistor is. And looking at these options, it is the thermistor D. So D is our answer. I always remember the ister part of the name is coming from the fact it's a resistor. And the therm bit, just like a thermometer or thermals, it's to do with temperature and heat. So really, when you understand what those parts of the word mean, it's really obvious that this is a thermistor. An object has a mass of 5 kilograms and it was falling in the sky. Here we can see the forces acting on this mass, and we're asked to calculate the acceleration of the object downwards. So the equation that's going to help us here is going to be force equals mass times acceleration, which is logical. We're given some forces which hold a mass, and we're asked to find an acceleration. This is the only equation we need. However, what are we going to use in place of the force? We need to realise that the force in this equation refers to the resultant or the overall force acting on this mass. If we look at it, we can see we've got 35 newtons down and 20 opposing that, acting up. It means we can work out the resultant force by taking that 35 and subtracting the 20. And we can see that overall we've got this resultant force equal to 15 newtons acting downwards. We also know the mass is equal to 5 kilograms, and that is in the right units. We don't need to do anything with that. So now looking at the equation, I can see we need acceleration. So let's rearrange this now to get acceleration on its own. We're going to divide through by the mass and get force divided by mass. Remember, it's the resultant force we use. So we've got 15 divided by 5, which just gives us 3. So our answer here is C, 3 meters per second squared. We've got a 1000 watt television watched for 6 hours. Here we're asked to calculate the energy transferred. And notice all of these energies aren't in the standard joules, they're in kilowatt hours. So that means that when we find an equation for this, we need to keep the units in kilowatts and hours to get these kilowatt hours. So let's find the equation we need. We need energy transferred, we need power, which is the watts, and time, which is the hours. So here we have energy transferred equals power times time. That's the equation we need for this. But like we said, because the energy needs to be in kilowatt hours, our power needs to be in kilowatts, and our time has to be in hours. Now this is a very rare time when we're going to convert away from the watts that we're given into a different unit, in this case kilowatts. So 1000 watts is equal to 1 kilowatt. We get that just by dividing through by 1000. Whereas the time is 6 hours, and that is what we want. So here we're going to do 1 for the power times by 6, which gives us 6 kilowatt hours. So our answer to this one is A, 6 kilowatt hours. A person weighs 700 newtons on Earth. We're told that on Earth the gravitational field constant is 10 newtons per kilogram, and on the Moon the gravitational field constant is 1.6 newtons per kilogram. Here we're asked to use this information to calculate the weight of this person on the Moon. So there's a little bit going on here that we need to think about. It's not an easy question this, there's going to be a couple of different steps. The first thing we need to do first is just identify what equation is going to be relevant. I want us to use the equation that weight is equal to mass times gravitational field strength. Now, you may be more familiar with this, instead of it saying weight, as saying gravitational force is equal to mass times by the gravitational field strength. They are exactly the same because, of course, the weight of an object is its force due to gravity. So let's have a look at the information we know about Earth. We know the person weighs 700 newtons on Earth, and therefore that is their gravitational force. We also know the gravitational field strength is equal to 10 on Earth. So that means that we've got enough information to work out the mass of this person. And the mass does not change whether we're on the Earth or the Moon, that stays the same. So that's the key to this question, finding the mass of this person and then using that to work out their weight on the Moon. Well, rearranging this equation, we find that mass is equal to the gravitational force divided by gravitational field strength, which gives us 700 over 10, which is 70 kilograms. So now we need to calculate their weight on the Moon. Here all we need to do is to plug in the numbers into our equation again. The mass is 70 because again, that's the same whether we're on the Moon, the Earth, anywhere. And we times it by 1.6. And that gives us 112 newtons for the weight of this person, which is option B. So that is all we need to write to get our answer. The circuit diagrams below show 4 different arrangements of identical resistors. Identify which arrangement has the highest resistance. Now, what's really important for us to know here is that when we place resistors in parallel, what we do is we reduce the overall resistance. They're less actually then than the individual resistances, and that's because you've given this current more options as to where it can flow. Therefore, in B, C and D, in each of these we have parts of it that have parallel regions. In B you can see that all of it is parallel. In C you've got this chunk in parallel, and in D you've got these 2 regions which are parallel. The only one out of all of these that doesn't have any parallel regions is A, which simply has 3 resistors in series. Now, as a result of this, the arrangement with the highest resistance is going to be A, because it is just in series, no parallel regions, and therefore we just add up those resistors to get the total resistance. So A is our answer. Miles per hour is a commonly used unit of speed. In physics, SI units are used. The SI unit for speed is meters per second. Here we're asked to identify which of the following speeds is approximately equal to 60 miles per hour. And we're told that 1 mile is equal to 1,609 metres. Now, by converting units like this, I like to think of it as 60 miles per, so divided by 1 hour. So we need this in metres per second. So what we need to do is to convert the 60 miles to metres and convert the 1 hour to seconds. Well, we're told that 1 mile is equal to 1,609 metres. To get 60 miles then, all we need to do is to take this 1,609 and times it by 60. That gives us 96,540. And that's how many metres 60 miles is. Now let's convert the hour to seconds. So there's 60 minutes in an hour and 60 seconds in each of those minutes. So that means 60 times 60 is the number of seconds in an hour, and that's 3,600. So 96,540 divided by 3,600 gives us 26.8 metres per second, which of course, out of all of these options here, the closest one is going to be 27. So A is our answer. A current carrying a wire was placed between 2 magnets. The magnetic flux density between the 2 magnets is 0.2 Tesla. We're asked to identify the force and direction of the force acting on the wire. Now, to work out the direction of this force, we're going to have to use Fleming's left-hand rule. So before we get our fingers out and start doing this, let's remind ourselves of that rule. It's a really important one. So first off, let me do my best at drawing a nice hand in the correct position. So we've got our thumb, we've got our forefinger, and then we've got our second finger. And then of course our third and fourth fingers all curled up there. So I did my best there. So now let's think about these fingers and thumbs. They're all going to be at right angles to each other. That is critical to you getting this right. We need to know that the thumb represents the force, or we could say the motion of this wire. We can see the M in motion kind of tallies with the M in thumb. Kind of clutching at straws, that one, but it's the best we can do. So now let's have a think about our first finger and what that is going to represent in this question. So the first finger represents the magnetic field. So here we're using the fact that field begins with an F and first begins with an F. And our second finger represents the current. So like I mentioned before, we can remember that the first finger represents the field by using the fact they both begin with an F. And we can remember that the current is shown by the second finger because there's a C in the word second. So now that we know all that, let's have a look at our diagram. We should know that magnetic field always goes from north to south, another really important fact. Because now what we can do is we can sort of summarise the information that we know here. Because by looking at those magnets, we've said that the field is acting downwards. We can say that our first finger needs to point downward. Because the current, as you can see on the diagram, is pointing from left to right, we can say our second finger needs to go left to right. So this is where we get out our left hand. Make sure it is your left hand. I remember making this mistake many times. And let's point our first finger down and our second finger from left to right. If you look at where your thumb is pointing, make sure again that they're all at right angles to each other. Your thumb should be pointing downwards. I always find rotating my wrist is the best method rather than trying to move my fingers. My wrist is the key here. So because we know that the thumb is going downwards or into the page, we can eliminate the two that say upwards. And that narrows us down to the force on the wire that's going to be the thing we need to work out next. So the equation we need to know here states that the force on a conductor is equal to the magnetic flux density times by the current and times by the length of the conductor in that field. So looking at this here, I can see that the force is going to be equal to 0.3 for the magnetic flux density times by 0.45 for the current and then times by the length. Now this is going to be 12 centimetres. We need metres though, that's 0.12 metres. So here we have 0.3 times by 0.45 times by 0.12, and that gives us a force on the wire equal to 0.0162. So as a result here, we can see that our answer must be A. So that is what we write in our answer box. Here we're asked to identify which of the following statements is the correct definition for inertia. And here we have just simply a recall definition type question. So the inertia is how difficult it is to change the velocity of an object, whereas the inertial mass is the ratio of force over acceleration. Well, here of course we just want inertia, so our answer is going to be B. Inertia is how difficult it is to change the velocity of an object. Now if you weren't familiar with these, this is the perfect opportunity to write down these two definitions, one for inertia and one for inertial mass. If you get learning these will be such easy marks in your exam. The graph below shows the heating curve for water. It shows how the temperature of water changes as the energy absorbed increases. We're asked in this question to write down the value of A, which is the temperature. So to answer this, let's just evaluate this diagram, okay? So you can see that X is found at negative temperatures. And because it's negative temperatures, it means it's very cold. Now that to me tells me that X is actually ice or solid water. Y therefore is going to be liquid water, and Z is going to be gaseous water or steam. So by recognising those different states, we can see that it's when Y changes to a gas. That's the temperature that we're looking for. And we should be familiar with the fact that water boils and changes to gas at 100 degrees C. Here we're asked to explain what the horizontal regions on the graph show us. So I've included this diagram here for us to look at. So here are the horizontal regions we're being asked about. Now notice that those horizontal regions, the temperature is constant. The temperature isn't increasing at all at those points. The reason why the temperature is constant here is because these are the points where we get changes in state. Now this means that we're going to have the energy being used to overcome the intermolecular forces of attraction between the particles. Now this means that the energy isn't being used to increase the temperature of this substance. The energy is just going towards overcoming those forces of attraction. Now this question here is a 2-mark question. So to be able to get those 2 marks, we need to state 2 key points. I think the most important of all these options is the fact that there are changes in state. We should just understand that of the horizontal regions. But then any explanation as to why the temperature doesn't increase would be your second point. So either we could say energy is being used to overcome the forces of attraction between those particles, or we could say that their energy is not being used to increase the temperature. Either of those can get you your second mark. So now we're told that the water is in different states at points X, Y and Z on the graph. In each of these states, the water has a different density. Here we're asked to explain the differences in the density between the states found at points X and Z. Well, from earlier, we evaluated that X must be a solid because it's very cold temperatures, whereas Z is the gas. Now, any changes in their density are going to be due to these different states. So we can state that Z, the gas, is less dense than X, the solid. That's our first statement that we can make. And now we can get on to explaining why that is the case. So because Z is a gas, the particles are much more spread out than they will be in X, the solid. And therefore, what would be essentially the same mass of this substance is going to occupy a much bigger volume. And that's what's going to have that knock-on effect on the density. So this question is a 3-mark question, so we need to have those 3 points to get our 3 marks. The first thing we want to state is, of course, that Z is less dense than X. Just lay that out to begin with. Then we need to express that in the gas, the particles are more spread out. And then finally we conclude linking it back to density, which is of course mass over volume, and make it clear that although we have the same mass, in the gas it occupies a much bigger volume, which is why it has a smaller density compared to the solid. The density of solid water ice is 916.7 kilograms per metre cubed. Calculate the volume of a 2 kilogram block of ice. So this is a calculation question. We need to write down the equation that's relevant. Here we're being asked about density and volume. So that means we're going to use the equation that density is equal to mass over volume. I always like to lay out the information they give me in the question too. So I've written down what the density is and what the mass is so that it's nice and neat and tidy. So now we know density is mass over volume. Now we need to find the volume. Now to do this, we need to rearrange the equation. Now you may be super comfortable with that, but if you're not, remember you can use the triangle. In this case, the triangle has mass on the top and density times volume on the bottom. The way they work is we cover up what we're looking to find, in this case the volume, and look at the triangle to see what the formula will be. So because it's m over d, the volume is equal to mass over density. So that's equal to 2 over 916.7. So there we are now, we've got our calculation. We just need to put that into the calculator, and that gives me 2.18 times 10 to the minus 3. Or you could give it a 0.00218. There you are, that is question D. The specific heat capacity of water in state X, Y and Z is given in the table below. Here we've got a nice table summarising everything, and we're told that the specific latent heat of fusion is 334,000 joules per kilogram, and the specific heat of vaporisation is 2,260,000 joules per kilogram. Now this question simply asks us to describe the difference between specific latent heat and specific heat capacity. So to be able to do this, really we just need to state the definitions of each of them. So let's see if you remember those definitions. If you don't, then pause the video after I've written them down and make a note of them yourself so that you're not wasting any time and you've got them down and you can get learning them. Alright, so let us get started with writing down the definition for the specific latent heat. So specific latent heat is the energy required to change the state of 1 kilogram of a substance. And that is the definition you need to know. You might hear specific latent heat of fusion or vaporization, but that is just looking at specific state changes going from solid to liquid or liquid to gas. So now let's look at specific heat capacity. Specific heat capacity is defined as the energy required to increase the temperature of 1 kilogram of a substance by 1 degree C, or you could say by 1 degree Kelvin. That is the definition that we need to know for specific heat capacity. It's a little bit longer than specific latent heat because we're talking about a specific temperature increase rather than just a change in state. But I think it's quite memorable, it's quite logical. Both definitions are referring to 1 kilogram of a substance. It's just that specific latent heat is looking at the energy required to change the state, whereas specific heat capacity is looking at the energy required to increase the temperature by 1 degree C. A beaker was filled with 200 grams of 25 degrees C liquid water and placed over a Bunsen burner. Here we're asked to calculate the total energy required to boil all of the water in the beaker. Now this is a clever question, okay? Total energy required. We need to consider here that we need to increase the temperature of that 25 degrees C liquid up to 100 degrees. Then we're being asked about boiling it all as well. So as well as increasing the temperature from 25 degrees C to 100, we also need to work out how much energy we need to boil 200 grams of water. So to change the state from liquid to gas. So it's a sneaky question, and I think it'd be very, very easy for students to miss that final step. So let's have a think about this then, okay? Let's first start with working out the energy needed to increase the temperature from 25 to 100 degrees C. So the equation for this is that the heat energy equals mass times specific heat capacity times by the change in temperature. And that's the equation that I've written down here. So to get that energy, we need to have the mass. Now we have 200 grams of water, but we need to convert that to kilograms. So dividing by 1,000, we get 0.2 kilograms. We then need to have a think about which specific heat capacity to choose. Now, because we're talking about liquid water, and we know that Y is referring to the liquid state from earlier, we can say that the specific heat capacity for this question that we need to use is 4,186. So now we need that change in temperature. Now, we know we need to go up to 100 degrees C to boil it, and it's currently 25, so that means that the change in temperature is 75. So that means that the energy transferred is going to be 62,790 joules. So we've done the first part of the question now, and we have some marks for doing that. Now we need to work out how much energy it will take to change the state of 200 grams of liquid to gas. So in this case, the energy is equal to mass times by specific latent heat. And earlier we were given two different specific latent heats. We were told the specific latent heat of fusion or of vaporization. Now, because here we're talking about boiling the water, that means that we need to use the specific latent heat of vaporization, because that is looking at the state change between liquid and gas. So the value of that we were told on the previous page is 2,260,000. So that's the value we're going to use in place of specific latent heat here. So the energy is going to equal 0.2, because we have 0.2 kilograms of water, times by 2,260,000. Now that leaves us with an answer of 452,000 joules. So here we have our two different sections of energy that we need. We know the energy needed to raise the temperature 100, and then we know the energy to change the state of it all to gas. So what we need to do finally to get our final answer is we need to add these two together. So adding these two together gives me 514,790 joules. So that there is our final answer. That's a really clever question. So if you get something like this in the exam, now you know exactly how to handle it. Train X was travelling between two stations, Station A and Station B. Train X was stationary at Station A. It then increased its speed to 50 metres per second over the next 40 seconds. The train then continued its journey at a constant velocity for 1.5 minutes, before decelerating for 30 seconds until it stopped at Station B. Here we are told that we can assume that the train had constant acceleration and deceleration. Here we're told that we need to complete the velocity time graph to start us off. So you can see they've started it off for us here. We've got the fact that it increased its speed from rest to 50 metres per second over the first 40 seconds. This is where we need to now finish it off. So we're told that the train continued its journey at a constant velocity for 1.5 minutes. Well, the graph's in seconds, so we should state that 1.5 minutes is equal to 90 seconds. We can also see that it finished accelerating at 40 seconds. Well, 40 plus 90 gives us 130 seconds. And the reason why I've done this is because I know that the train continues at a constant velocity, so we're going to get a horizontal line, but we need to know for how long. I now know it's going to go on until 130 seconds. So then we've got the next part of the journey. We're told it decelerated for 30 seconds until it stopped at Station B. So 30 seconds of deceleration, constant deceleration the question said. So we're at 130 seconds now, plus 30 seconds gives us 160 seconds. So I'm going to draw now a diagonal line down from that point where we were, down to 160. And that there is my completed velocity time graph. Now in B, we're asked to calculate the acceleration of the train in the first 40 seconds. Now, we should understand that we calculate acceleration from a velocity time graph by working out the gradient of that graph. And here, because we're looking at those first 40 seconds, we need to find the gradient just of that region there. Well, we know that the gradient and also the acceleration is calculated by finding the change in velocity, which is a change in that y-axis, divided by the change in time, which is the change in the x. So the change in velocity is 50 minus 0, and the change in time is 40 minus 0. That simplifies to 50 over 40, which gives us 1.25, and that is our acceleration in meters per second squared. So now we're asked to calculate the total distance between station A and station B. Now again, we need to understand that when we have a velocity time graph, we can work out the total distance travelled by working out the area under that graph. Now here, because we're looking at that whole journey, not just a part of the journey, we're looking at it going from A to B, which is the beginning of this journey, to the end of it, we need to work out that total area. Now, we can do this in two different methods. It just depends on what you're most comfortable with. First method is that we could recognise that we have a trapezium shape here, and we can use the trapezium equation to work out the area of this shape. And the area of a trapezium is the height divided by 2 times by A plus B. Alternatively, if you don't like that, if maths isn't your favourite, you could split it into 2 triangles and a rectangle. And that should be an easy enough method too. Both of them will get the same answer at the end. So I'm going to use the trapezium equation here. So if I label on what I know here, the height, the h of this equation, is going to be 50. The A and B are the 2 parallel sides. So A is going to be this top side here, which goes between 40 and 130, so that's 90 long. And along the bottom, it goes from 0 all the way up to 160. So that's going to be 160 long. So we could say B is 160. Now we can put the numbers back into our equation now. And we can say that the area equals h over 2 times by A plus B, which gives us 50 over 2 times by 90 plus 160. Like I say, this is just one method that you can use. If you use a different one, that's fine. So finally, putting that into the calculator, I get an area and a distance equal to 6,250 metres. Now for part D. In this question, it was assumed that the acceleration of train X was constant. In reality, the train's acceleration decreases as the velocity of the train increases. And here we're asked to explain why. So what we need to consider here is that as the train's velocity increases, the air resistance increases. Imagine, the faster you go, say if you're going for a run or something compared to walking, you can feel the air hitting you harder. And that's exactly what's happening here to this train to a much bigger scale. So now that we have this bigger backward force, the effect this is going to have is it is going to subtract from the thrust of the train. So that's going to mean that the overall force acting on this train is going to get smaller, which means that our resultant force on the train gets smaller. Now, of course, we know, due to the equation F equals ma, that force is directly proportional to the acceleration. And therefore, we can conclude here that as the force is getting smaller, the acceleration will also decrease. And that there is the answer to our question. There are our 3 key points that we need to include to get our 3 marks in this question. In this question, it's been assumed that the acceleration of train X was constant. However, in reality, the train's acceleration decreases as the velocity of the train increases. Here we're asked to explain why this happens. So this is a 3-mark question, so we need 3 good points. The first thing that we want to state is that as the train's velocity increases, the air resistance increases. Think about it, if you go for a run compared to walking, the air and the wind is all in your hair, pushing it back. There's a bigger air resistance the faster you go. So by increasing the air resistance, that means that we're increasing the backwards force on this train. And as a result, we decrease that overall or resultant force acting forward. Now this is important because resultant force and acceleration are linked. Don't forget the equation that states that force equals mass times acceleration. Force is of course proportional to acceleration via that equation. And as a result, the acceleration decreases. And those are our 3 key points that we need to make to answer this question fully. Another train, train Y, has a graph of its distance travelled with time plotted. The graph below shows how the distance travelled by the train changes with time. Here we need to use the graph to find an estimate for the speed of this train at 20 seconds. Now normally if you have a distance time graph and you want to find the speed, you work out the gradient of that line. However, this is a curve, and so we've got an extra step to include here. To start us off, we're going to need to draw a tangent at the point that they're talking about, so at 20 seconds. And then once you've got that tangent drawn on, we need to find the gradient of the line. That's why this is an estimate, because it relies on our tangent. Everybody's tangent is going to be ever so slightly different, so there will be some leeway in your answer here. So let's get started then, and let's draw on the tangent. Remember, a tangent is a straight line that just touches the point. Make sure you use a ruler and a pencil as always. So now that we've done that, we've drawn the tangent, let's work out the gradient. I'm drawing a little triangle here, and I want to do the biggest triangle possible. So I know that the gradient is equal to the change in the y-axis divided by the change in the x-axis. Looking at the little triangle that I've drawn here, I can say that the change in the y is going to be equal to 1,200 minus 240, and the change in x is quite simply just going to be 40 minus 0, which is just 40. So popping this into the calculator, I need to find 960 divided by 40, and that gives me 24 meters per second. So here, when we're asked to use the graph to find an estimate for the speed of the train at 20 seconds, all we need to do is to draw a tangent at that 20 seconds, find the gradient of the tangent, which involves doing the change in y over the change in x of a little triangle within that tangent, put the numbers in, and then I get 24. But again, this is an estimate question. And because it's an estimate, everyone's going to get slightly different answers. Here the mark scheme allows any answers between 23 and 27.5. So there's a good range of answers available there. But yeah, I hope that makes a lot of sense. If you're not familiar with the fact that the gradient of a distance time graph gives us speed, that the gradient of a velocity time graph gives us acceleration, and of course that the area under a velocity time graph gives us distance travelled, then make sure you make a note of those now and get learning them. Good work. Light-emitting diodes have many uses. They're used in many electrical devices, including remote controls and traffic lights. Here we're asked to describe what a diode actually is. And this is a little definition that we need to know. So if you don't know it, get yourself out a flashcard now and copy it down with me. So a diode is a component which only allows current to flow in one direction. And that's all we need to write down there to get our mark. In this question, we're talking about light-emitting diodes. So if we were asked about a light-emitting diode, then we would still give the same definition, only we would add that light is emitted in this process too. Next up, we're asked to describe the energy transfer that occurs in an LED, a light-emitting diode, when it's connected to a circuit with a power supply. So here we need to know what it begins with, and of course initially it's connected to a power supply, so it has electrical energy to begin with, and then it transfers it to light energy, and that's why it can emit light. So we can say that in a sentence, or we could write it like I have here, but you would get your 1 mark either way. Now we're asked to sketch the IV graph for a light-emitting diode. So there's a few of these that we need to know off by heart, perfect for flashcards. For a light-emitting diode, or any diode for that fact, the current stays very close to zero for negative potential differences, and only when it becomes a positive potential difference does it begin to increase. And then it increases with an increasing gradient. And don't forget, the reason why it stays so close to zero, that current, for negative potential differences, is because of that definition of a diode, the fact it only allows the current to flow in one direction. And we're seeing it here in this graph. So here we have a big 6-mark question. We're asked to describe an experiment that will find the IV graph of a light-emitting diode. And we can use a circuit diagram in our answer, and I think they're a really useful way to aid our explanation. So let's start off by drawing our circuit diagram. Now, the first thing I'm drawing is the symbol for a light-emitting diode. So what we have here is this triangle with a line against it with 2 arrows pointing away. That's because it's a light-emitting diode. A diode alone wouldn't have those arrows. Then we have that diode connected in series with a power supply and also an ammeter. Then we're going to place a voltmeter in parallel. Now, the reason why we have that ammeter is to measure the current in this experiment. And we always want to have ammeters in series with the component that we're measuring. So then we also have a voltmeter, which is the circle with the V in it. Now, voltmeters always need to go in parallel with the component that we're investigating. And the whole point of a voltmeter is to measure the potential difference or the voltage in the circuit. So there's one last thing that we need to add to this circuit diagram that we're missing at the moment. So we need to have a way to vary the potential difference. And the way that we're going to do that is by adding a variable resistor. A variable resistor looks like a rectangle with a diagonal arrow going through it. So now we've got this circuit diagram set up, and by drawing it and labelling it well, already actually we've got quite a good chunk of these marks in this question. So now let's describe what we're going to do. So once we've set up the apparatus in this way, we're going to record the potential difference and the current. Once we've done that, we're now going to use our variable resistor to change the potential difference. Once we've done that, we're now again going to record the new potential difference in current. Again, we're going to use our voltmeter to measure potential difference, and we're going to use the ammeter to measure the current. Now we're going to use that keyword that we use in so many of these investigation questions. We're going to repeat this process, because the more we repeat it for slightly different potential differences, the more data points we'll have for our graph. Now, once we've done this, we'll notice that we're only getting positive potential differences. So we're only really getting half the graph. What we need to do now is reverse the power supply. By reversing the power supply, we're now going to get negative potential differences. And now we're going to repeat the process before of recording the potential difference and the current, and then using the variable resistor to change the potential difference and repeat. So once we've done this now, we're going to have many data points for both positive potential difference and negative potential difference. So now all we need to do is plot a graph of current against potential difference. And this, of course, was the aim of the game. When we go back to the question to reread it to check that we've got everything down, you can see that we were asked to describe an experiment that would find the IV graph of a light-emitting diode. We've done that here. So you see there's a lot of points we can say here. In these 6-mark questions, we don't want to limit ourselves just to saying 6 points. In any other question, that's a fine method, but these 6-mark questions, instead we're being marked slightly differently. We need to make sure that we give as full an answer as possible and not just giving a few points that we'll do at the beginning of the experiment. We make sure that we talk our whole way through from the beginning, the middle and the end of this experiment, and we talk about any apparatus and measurements that we need to take. So there we are. This would be our perfect model answer. This is a very common question, so by all means, get writing this down and get learning this.
A dynamo is a direct current generator. Some bicycles use dynamos to generate electricity to power their lamps while the bicycle's wheels are turning. So here we've got a nice little diagram here. You can see we've got this split ring commutator and brushes as well. and we're asked to describe how the dynamo induces a current in the wire. Now this is a 3-mark question, so we need 3 good points to explain this. This is one of those quite tricky questions, so if you're not 100% of this already, then use this as an opportunity to get these down on your flashcards right now. Okay, so the first thing that we're going to state is that the coil is going to move through the magnetic field, or we could state that it cuts through magnetic field lines. As our first point here. Okay, so on to our second point. So we should be able to state that therefore a potential difference is induced as our second key point that we need to say. And then finally, because the question's asking about how it induces a current in the wire, we're going to state that because we have a complete circuit here, a current is induced. And those are our 3 key points that we need to state to get our 3 marks here. So if you're not familiar with this, then get out a flashcard, pause this video now, and write it down. Now we're asked to explain the importance of the split ring commutator. And this is a vital part of a dynamo. So this is a 2-mark question. We need 2 key points. I'm going to write down 3 points here, but pick whichever 2 you're the most comfortable with. So the split ring commutator is able to change the coil connections every half turn. Now, this means that as the induced potential difference is about to change direction, the connections get reversed. Now, the consequence of this is that when we induce this current, it always flows in the same direction, which means that this dynamo is inducing a direct current. So these are 3 key points that we can say to be able to, of course, get our 2 marks. We only need to state 2 of them, the most suitable 2 that for you makes sense. However, it's always good to learn all of them because, let's be honest, today it's a 2-mark question, tomorrow it could be a 3-mark question. And if you only learn the bare minimum in a question, then you're not setting yourself up for that worst case scenario, that most challenging question. So there we are. There are our 3 points we could write down to explain the importance of the split ring commutator. So for part C, we're asked to complete the graph to show how the induced potential difference varies with time as the coil moves through one complete rotation of the coil in the dynamo. We're assuming that at t equals 0, the coil is moving parallel to the direction of the magnetic field. Now, when it's parallel to the magnetic field, there's no field lines getting cut. So as a result, if we think of what we said in A, if there's no field lines being cut, then there's no potential difference being induced. So at 0 time, there's 0 potential difference. It's then going to go up to a maximum and then down back to 0. And it's not ever going to go negative because with a dynamo, it's making a direct current. It's just going to bump up again. So if we just think about what each of these mean. Initially, the coil is moving parallel to the direction of the magnetic field. Now that means if these pink lines are the field, that there's no field lines being cut, and therefore there's no induced potential difference. However, when it's rotated to 90 degrees, what we have now is we've got the maximum amount of field lines being cut, because that motion is perpendicular to the field lines. So that's why at what would essentially be when it's at the orientation 90 degrees, we have a maximum. Then it bumps back down to 0 because then when it gets to a 180 degree rotation, we're back at square one essentially, just upside down. We can see that the coil is moving parallel to the direction of the magnetic field. So then again, we'll be at essentially 270 degree rotation now. We can see again, we're essentially sort of back to that orientation where it is moving at right angles to the field. So we've got a maximum induced potential difference. And then finally, we finish up back 360 degrees at that start point. And so we finish on 0 because we're back to being parallel to the direction of the magnetic field. Now, we can of course just learn the graph as it is. However, I think it makes it make more sense if we can think about what's happening. Now, all that I was trying to explain with these little diagrams is that we need that motion to be perpendicular to the field lines to get the maximum induced potential difference. And if they're parallel, then no field lines are getting cut at all, and we get zero potential difference. So now we're asked to state one change that can be made to increase the size of the induced potential difference. There's two things we could say here. We just need to state one, but it's worth learning them both. So the first thing we could say is we could just use stronger magnets or a stronger magnetic field. That is certainly going to increase the size of that induced potential difference. Secondly, we could increase the frequency of rotation. What both of these things are doing are increasing the number of field lines being cut any second. Through stronger magnets, that's because there's more field lines, they're going to be closer together. Whereas when we increase the frequency of rotation, what we're doing there is we're moving that coil more quickly, which means that in any second, it's going to cut more of those field lines because it's going to rotate through them more times. So both of those are good ways we could increase the size of the induced potential difference. So for the last part of this question, we're told that dynamos generate direct current and alternators generate alternating current. We're asked to suggest what changes could be made to a dynamo to convert it into an alternator. So there's one simple change that we can make here, and that is replacing the split ring commutator with slip rings. Now that is going to be all you need to do to now have an alternator rather than a dynamo. And the reason for this change is, of course, remember we wanted the split ring commutator to be able to reverse the connections every half turn. We don't need that now when we have an alternator where we're making this alternating current. So as simple as that, perfect for a flashcard. How do you change dynamo to an alternator? Replace the split ring commutator with slip rings. A starting pistol is fired to start a race. The mass of the bullet is 9 grams. The pistol has a mass of 0.7 kilograms. When it is fired, it's observed to recoil back at a velocity of 5 meters per second. Velocity is a vector quantity. Here we need to describe the difference between a vector and a scalar. Now this here is a very classic question. We do need to make sure that we know this difference, so it's easy marks. If you don't know it, this is time to put it onto a flashcard. So we should recognise that a vector has magnitude, so size, and direction, so it could be going up, down, left, right, whereas a scalar only has magnitude. It doesn't have any direction at all. So it just tells us how fast we're going if we're talking about speed, but it doesn't tell us where we're going, which the velocity would also tell us. So there we go, that is our differences. That's all we need to say to get our 2 marks. And if you don't know that, just put that on a flashcard now. Here we're asked to calculate the momentum of the pistol as it recoils. So let's start off by reminding ourselves of the equation for momentum. We need to know that momentum is equal to mass times by velocity. And that's what we're going to use here to calculate this momentum. On the previous page, we were told that the mass of the pistol was 0.7 kilograms and its velocity when it recoiled was 5 meters per second. So we can put those numbers now into this formula, and we can say that momentum equals 0.7 times by 5, which gives us 3.5 kilogram meters per second. So in the next part of the question, we're asked to explain why the pistol recoils. And this is a 3-mark question, so we need 3 points. So the first thing is simply due to the conservation of momentum. That is the crux of why it has this effect. So now we need to understand that when we look at this conservation of momentum, before we fired the gun has to be equal to the momentum after we fire the gun. And before we fired the gun, the velocity of the pistol and the bullet was just 0. So the momentum before firing was just equal to 0. Now that must mean that for the after momentum to also equal 0, the momentum of the bullet and the pistol must be in opposite directions, because that's the only way that the total momentum could equal 0 after firing. Essentially, one of the momentums will be positive and the other one will be negative as it's in the opposite direction. So those are our 3 key points. Let's just summarise them one last time. So first thing we want to state is that we have conservation of momentum happening. Then we should understand that before we fired it, the momentum was equal 0. And our final point here is that the bullet and the pistol must have momentum that is in opposite directions so that the total momentum is equal to 0 after firing that gun. So now let's have a look at the last part of this question. In a different race, a heavier starting pistol was used. A 9-gram bullet is used again, and the bullet reaches the same velocity when fired from each pistol. Explain how the motion of the heavier pistol will compare to that of the lighter pistol when fired. Well, what we need to think about here is the fact that the momentum has to stay the same because that initial momentum hasn't changed. So the result of this is that the pistol will actually move back or recoil more slowly. And this is because that initial momentum has stayed the same, and therefore using the conservation of momentum, we know that the final momentum is also the same as it was. And in this case, we've got more mass, which means that we must decrease the velocity. So, in explanation of how the motion of the heavier pistol will compare to that of the lighter pistol, we have 2 points. One is that the pistol will recoil back more slowly, and the second is just explaining why this is, the fact that it's because the momentum is the same, but the mass has increased. So that is our answer. An investigation was carried out to find how the number of turns on a coil affects the strength of an electromagnet. A wire was wrapped around a large iron nail, and the wire was connected to a battery, as you can see in this diagram. This formed an electromagnet. The number of paper clips that the electromagnet would pick up was recorded, and the number of turns around the iron nail was increased, and the method repeated. A simplified diagram of the electromagnet is shown below. Here we're asked to draw the magnetic field pattern around the electromagnet. So here is the diagram that you need to draw. Now the key features that we need to include in this question. One of them is that the magnetic field lines have to point from north to south, and that's always the case. We should also know that the magnetic field lines are never going to cross each other. That will never happen. And it's also worthwhile knowing that the closer together the lines, the stronger the magnetic field. So as it's like leaving the ends of this electromagnet, you can see that the lines are closer together, and that's where the magnetic field will be stronger. So this is the general shape that you need to know. The magnetic field pattern around an electromagnet is exactly the same around a bar magnet. So if you learn it once, you know it both times. Now we're asked to explain why the field inside the electromagnet is strong. So the reason for this is that every little coil of this electromagnet is going to have its own magnetic field. And what's going to happen is the magnetic fields from all of the different coils are going to add together to provide you with a stronger magnetic field. And so that is your answer. The field inside the electromagnet is strong because the magnetic fields from each coil add together. The results were plotted on a graph. Here we're asked to start off by drawing a line of best fit. So here is my line of best fit. We need to make sure that whenever we draw a line of best fit, we use a ruler and a pencil. And it is a general guide to make sure that you've got around as many points above as below your line of best fit. However, there's always going to be a little bit of leeway with it, which is why any answers that are dependent on your line of best fit will allow a bit of leeway because you'll never ever get it perfect. You're not a computer. So now we're asked to predict how many turns on the coil would be required to pick up 5 paper clips. So if I now return to the graph and my line of best fit, I can see that 5 paper clips, if I read along and then down, corresponds to 130 turns on the coil. Notice we couldn't have done that if it wasn't for our line of best fit. Now, an important thing to remember here, though, is you might have got a slightly different answer to me there. It's really just going to depend on your line of best fit. It might be a little bit steeper, a little bit less steep. The mark scheme here will allow any answer in the range of 120 to 130. So there's a good range there. You don't have to get it perfect at all, okay? So that there would be my answer. Don't panic about getting the exact answer on the mark scheme because, of course, your line of best fit will be slightly different to the one written on the mark scheme. Now we're asked to explain the relationship observed between the number of turns on the coil and the number of paper clips it can pick up. So this here is an explain question. Obviously, we can see the relationship is that the more turns on the coil, the more paper clips can be picked up by this electromagnet. However, here, because this is an explain, we need to talk about the science behind it. Why is it that it increases? So for this 2-mark question, we need 2 key points. The first thing that we want to state is that more turns on this coil will induce a stronger magnetic field. That's the first point that we need to get across. Our second point is clearly making it clear that a stronger magnetic field means that we have a stronger force of attraction, and therefore we can pick up more paper clips. Now they would be the 2 points that we need to state to get our 2 marks in this question. Now we need to suggest a limitation of this experiment and give an improvement. Suggest questions can be tricky because there's no obvious answer, there's nothing that you've learned specifically for this. Instead, we need to use some general knowledge and some deduction. So in this question, we're limited by the size of the paper clips. We've only got 1 paper clip, 2 paper clip, 3 paper clip. What about if it could actually pick up half a paper clip or a third of a paper clip? We're missing out on that important information. So a way that we could rectify this and improve it is by simply using smaller paper clips. So now we need to suggest how the reliability of the experiment could be removed. And whenever we talk about improving reliability, let's always say, let's do some repeats. Finally here, we're told that electromagnets are used for door locks. And for a simple 1 mark here, we're asked to explain why. So the key feature of the use of electromagnets in door locks is the fact that they can be switched on and off. Because of course we need to be able to open the door again, don't we? We don't want it to be locked forever. Electromagnets, by turning the current on and off, enable you to turn the electromagnet on and off. So that's our answer to this one. That's all we need to say. A person is using a wheelbarrow as a lever to transport a load of mass at 20 kilograms. The weight of the wheelbarrow is 90 newtons. The person used an effort force of F to lift the wheelbarrow, and we're asked here to calculate the weight X of the load. Well, we should be familiar with the equation for weight. We should know that weight is equal to mass times by gravitational field strength. We should also be aware we're specifically in this question talking about the load, nothing else. So if we go through the question here, we can see that we're transporting a load of mass 20 kilograms. So in this case, we know that the mass is 20 kilograms. And we're also told in the question what the gravitational field strength is. We're told that it's 10 newtons per kilogram. So now that we have this, we can just put these into our equation for the weight. We can say that the weight is going to be equal to 20 times by 10. So that gives us 200 newtons for the weight.
So we can just pop it into our line here, 200 newtons. So here we need to calculate the size and direction of the moment caused by the weight of the wheelbarrow. Let's remind ourselves of the picture. So if we're just looking at the weight of the wheelbarrow, we should be familiar with the fact that that is the 90 newtons. So let's just circle that in here. We can also see that the distance from the pivot, which is at the wheel, and this weight is 0.5 meters. So those are the numbers we need. We need to know that the equation for the moment of a force is equal to the force times by the distance between that force and the pivot, which, like I said, in this case is that wheel. So in the equation that you get given, it does state that that distance is normal to the direction of the force. And that is really important. It has to be at right angles to the force. And you can see that we do have that in this question. So now we have everything. We can say that the moment is equal to the force, 90, times by the distance, 0.5. And that gives us a moment equal to 45 Newton meters. Now looking at this question, you can see that we're also asked about the direction of the moment. Well, if we bear in mind that that pivot is at the wheel, you imagine that the force is pushing it down, it is going to rotate in this clockwise direction. If I ever feel a bit confused in a question about moments, whether it's going clockwise or anti-clockwise, I always like to just get my pen, hold the pen where the pivot is with my little pinchy fingers, and then push up or down with my other finger at the other end of the pencil, sort of replicating the diagram. So if I do that right now, if I get my pen in front of me, I hold onto it with my thumb and my forefinger on my left hand, and I push down on the right hand side, kind of replicating that wheelbarrow force. I can see it's going to rotate around like a clock in the clockwise direction. So that's what I do if I get a little bit stuck, okay? So use that tip yourself if you ever feel confused. But what we're going to add in here is clockwise. So now we're told that given that the wheelbarrow is in equilibrium, calculate that effort force required to lift the wheelbarrow. So to answer this, we need to know that if a body is in equilibrium, the sum of the clockwise moments is going to be equal to the sum of the anti-clockwise moments. And that's such an important statement. That's only true when the forces are balanced or in equilibrium, depending on how they're phrasing it. But that's going to enable us to calculate this effort force. If we have a look at the diagram and try and work out, okay, so where are these clockwise moments and where are these anti-clockwise moments, then that's going to help us. So we've already determined, haven't we, one of the clockwise moments. We said that the pivot is where the wheel is, and we said that the wheelbarrow, and we can actually see now that also that load as well are going to cause this wheelbarrow to rotate in the clockwise direction. So those cause clockwise moments. Whereas we must have some anti-clockwise moments. Well, looking at this, we can see that the lifting of the wheelbarrow causes a force that generates an anti-clockwise moment. So here we have some clockwise moments and we have some anti-clockwise moments. We can work those out and put them equal to each other. So let's get started with the clockwise moments, and let's start with X, that load. We know that the weight, we worked it out in part A, was equal to 200 newtons, and that has a distance of 0.3 meters to the pivot. So one of the clockwise moments is 0.3 times 200. There's another one though, isn't there, caused by that 90 newton force of the wheelbarrow's weight. We've already worked out that moment though, it's 45 newton meters. So now let's work out the sum of those anti-clockwise moments. Well, there's only one. It's going to be 1.2 times by F, or you could write it as F times 1.2. So now we've done that, let's tidy this up. We're going to have 60 plus 45 Newton meters in the clockwise direction, which we can simplify to give us 105 Newton meters clockwise. That's equal to 1.2 times by F.
So we're nearly there now. All we need to do is rearrange this equation. F is going to be equal to 105 divided by 1.2, which gives me 87.5 newtons. So that is the size of the force F, that effort force required to lift the wheelbarrow and hold it in equilibrium. The person was offered a different wheelbarrow to lift the load. The new wheelbarrow had longer handles. The person was told it was going to take less effort to lift the load using this longer handled wheelbarrow. Describe and explain the effect this will have on the effort force required to maintain equilibrium. So this is a 2-mark question. So what we need to understand here is that clockwise moment isn't affected in any way by this difference in the handles. The clockwise moment is going to remain exactly the same because the weight of the wheelbarrow and the weight of the load has stayed the same. So that's going to be our first point here. The clockwise moment remains the same, and as a result, because this is an equilibrium, we need to understand that if the clockwise moment has remained the same, then the anti-clockwise moment will also remain the same. So now we need to think about our conclusion here. We need to realise that to maintain this anti-clockwise moment, which hasn't changed, if we have the distance increasing, then the force must decrease. And this is because, of course, moment equals force times distance. Force and distance are actually inversely proportional. So as one gets bigger, the other one has to get smaller to counteract that effect. So the key things that we need to get into our answer here to get our 2 marks is, firstly, we need to understand that the clockwise moment remains the same. And the second thing we need to say to get our mark is that in order to keep the anti-clockwise moment the same as well, the force must decrease. In a nutshell, that's all we need to say, but what I've given you here is the full answer so that it can actually make sense, and I really hope it does. So just to summarise, remember the clockwise moment is unaffected, it remains the same. However, it's still in equilibrium, so the anti-clockwise moment must also be the same. And finally, as we know that the distance between the force and that pivot has increased, the force must decrease. And that is us having described and explained the effect this would have on the effort force required to maintain equilibrium.
Well done for making it to the end of this paper, lovelies. I'm really, really proud of all of your hard work.